Hello everyone and welcome back to the last demo of the KMean clustering algorithm with synthetic data. We normally call it synthetic data in the language of research, where we produce these random numbers just to see the functionality of the algorithm, and then we move towards the real data sets or the more sensible data sets, which we can use to see how the clustering or how the algorithm is performing against the real data set, which is a normal research cycle, but obviously it has its own steps that we need to follow, right? So considering we are already looking it from the practical perspective, so that's why we just use the synthetic data set just to test the algorithm first, and once we are happy with the performance, we can switch over to the real data set, which we're gonna do in the upcoming videos. So this video is going to be very interesting. In this video, we're gonna see graphically how the K-mean clustering is converging to the local minima, where all the points which are closer to their respective centroid, they cluster around that centroid, and then we have this group formed. And seeing anything really that makes better sense than seeing it in the numerical format or textual format. So let's jump into the notebook. You can see it's the same notebook. The only thing I have made two changes. First, I did in the last video, we used the one-dimensional data. In this video, we are going to use the two-dimensional data, because we are going to apply the Euclidean distance formula. And if you remember, we have already discussed the Euclidean distance equation in the k nearest neighbor. The beauty is K-mean clustering is using the k nearest neighbor mathematical derivation, which is really helpful for us because we can use the same mathematical model and solve two different kind of problems. So that's why. So let me just first show you the function which we are using to sorry, that's the recalculation to calculate the Euclidean distance. So you can see we have the same function that we have used in the k nearest neighbor. We are subtracting the corresponding point. So if we have point which has two dimension x and y, so x1 is subtracting from y1, and x2 is subtracting from y2. And if we have n number of dimension within a point, then we obviously subtract to the corresponding dimensions in the formula. And once we subtract, then we are squaring them. So that's why we have the square. And then what we are doing, we are summarizing them, we are aggregating them using the summation function, and at the end we are taking the square root. So each dimension is subtracting from each corresponding dimension, and then we are squaring them, because if you can see, I'm multiplying the same expression with the same one, so that will convert into the square. And then obviously we are subtracting these the dimension from each other. So that means we are subtracting from x1 minus y1 square, right? And then we are subtracting we are adding x2 minus y2 square into it, all the way xn minus yn square, and whatever value is gonna return to us, we are taking the square root, and that will be Euclidean distance for us. Now that's the function which I have just added into this notebook, and now I'm going to show you where I'm calling it, because the new function will multi-dimensional. And by the way, this function is going to work with 2 to n dimension, so you don't need to change anything. That's something you need to keep in mind. So what I'm going to do, you can see I'm passing my centroid point and the point which I'm getting from the data set. I'm just passing these points to my new function, calculate Euclidean distance, and then whatever value is coming back, I'm storing it into EU distance. And then the logic remains same, like I'm checking whether the EU distance, if it is less than the existing minimum distance, swap the minimum distance with it, change the index, change the cluster ID index, and obviously then the rest of the process remains same, that we keep running it based on all centroid, and whichever centroid is going to be closer to my point, that centroid is going to be used as a identity to define the cluster, right? So obviously, like you can see, I'm passing k is equal to 3, so I'm actually clustering into three different cluster in this function, right? I've already explained the whole function in the previous video. I'm going to put that link in the video description. Please watch if you don't understand this function. The only difference in this function is going to be this statement that I have replaced and adding the Euclidean distance. Right. There is some changes in the recalculation of the centroid as well. You can see I'm also instead of printing, I'm calling now the scatter plot because I want to print it. So how that logic works, let me just show you. As soon as we enter in the into the function, and by the way, I have two versions. One is the textual one. I'm going to show you. It just print the textual log just to print the textual values or numerical values on the screen. And the other one is the graphical one. So you can see as soon as we enter into the function, that part is same. But now I'm printing all my points into with a black color. So you're going to see all the points are black. And why I'm doing it, because later on I'm going to actually change the color, and I'm going to just put the centroid with black color, so you can see the closeness of the point to the center, and how the coloring is showing the boundary of the cluster of these points. Okay, the next thing, the loop will start, and once my whole clustering algorithm work, where I'm actually allocating the cluster to my point, I'm just printing my cluster based on the cluster ID. So sorry, based on the cluster index, I'm picking the value from the color. So I'm passing this array into my function, and obviously if cluster 1 has the index 0, so whatever color I'm passing as 0, for example, I'm passing red at 0 index, that color is going to assign all those points which have the cluster 1 allocation. Similar, if I'm passing 1 as a second index into my array, so it's going to actually check whatever value on the second index in my color array, and it's going to actually pick it from there and assign to that color to all points which sits into the second cluster, and then the routine goes on. But the beauty is that at the end, once the loop will finish, you're going to see a very nice color distribution on your graph, where point shows that how these points are clustering with each other. All right, so what I'm going to do now, I'm just going to show you one thing before I come back to the function. If I can minimize. Now I want to recalculate. Keep that open. This one I can. I'm just minimizing those cells which I don't need at this point. Recalculate, I need it. Yeah, so that's the color array that I've defined. You can see I've already defined 4 color: red, green, blue, and yellow. And you can see I'm passing, because I'm passing the value of k as 4. Let me just make it more meaningful so you can see k is equal to 4. Max iteration, I'm actually doing 10, right? And then array. So what I'm going to do now, I'm just going to and let me see if I can, redefine that. Yeah, I think that's better, because that will clear the output. So it will help us to see the output again. Now, That's all good. I'm not going to run this statement because that will start the process. I will come back to it once I finish the explanation of the algorithm. Now, in the case centroid, recalculate centroid, the only difference, because previously we only have one dimension, so that's why we are subtracting them straight away. Now, what we are, sorry, we are calculating the mean by just adding those points and dividing it by 2. But now, because we have multiple points, so what we're gonna do, instead of passing the key, so now that's where keep in mind I'm actually swapping the value, because now my value is an array. I cannot use my array as a key. It won't allow us in Python or PySpark, because we need to hash to convert it into a value, and then that value can be used as a key, right? So that's why what I'm doing, I'm actually using the cluster ID of the point as a key, and then I'm storing it, storing the value of the point, because it can be two-dimensional point, it can be three-dimensional point. I'm storing it into the value, and I'm extracting that value. So now you can see my centroid, that is also a multi-dimensional point. So I'm just adding them. What it will do, it will add similarly the same dimension into each other, and then sum them up, and at the end I'm dividing it by 2. Just the normal calculation of mean, which I've already explained in the previous video. So that's the only difference I have made in the recalculation of my centroid. All right, so these two things are done. So these three things, including I've discussed the color scheme, I've discussed the changes in both function and the Euclidean distance that I've introduced into my algorithm. Now, what I'm going to do, let's start with simple. Let me start with 100 points randomly, and I'm changing the shape, because now we don't have single dimensional array. I'm changing it to multi-dimensional array. By the way, you can go to the high dimension, but unfortunately you cannot show them on the graph. So the graph you can only show up to 3-dimensional if you have the 3-dimensional support available into your graphic, right? So but in this video we are only limiting ourselves to 2-dimensional, right? But the same function, everything remains same in the high dimension, except you cannot display on the screen. All right, now generating the number. So we have now our data set, which I'm storing into P dataset. And now I'm going to define, we have already run this cell, but just to show you, we are defining the color. I'm passing, because I want to create 4 cluster of my point. So I'm just passing the value of K to 4, and I'm passing the iteration as 10 to, just pass the maximum that we can see whether it's going to be converged or reach to the local minima within those 4 iteration, right? And I've already discussed the concept of iteration in my last video. Excuse me. So let me run it. The variables are defined, and now we are going to call our actual function, calculate K cluster. First parameter is the data set. The second parameter is the number of K. The third one is the max iteration. And the last one is the K color, because we want to graphically cluster our points. Now let's run it, and we'll wait to see how it goes. So you can see the iterations are pretty quick because we have less data set. Now that's something that we are looking to see. Let me start from the top. Yeah. So you can see my after first iteration, because these points are random picks. So I have just picked 4 random points. So you can see the distribution of the clustering based on these points are not very intuitive, because it was just like random picking first 4 points and then starting the algorithm. But as soon as we jump into the second iteration, you can see how efficiently the points have been changed, because we have recalculated the centroid based on the points, and based on the recalculation of these centroid, our points have been adjusted, and you can see this point has now changed to come to here. So it will be more centralized to these points, but there's still some some points which are not properly allocated. That's why you can see we still have changes. You can find it out in the centroid value. Like you can see, let me show you. That's the first iteration where our first centroid is 5312. That's the XY dimension. Second point is a second centroid is 8795, third one 63.4, and the last one is 53.32. Now, once we recalculate the centroid or recalibrate, because we have these four clusters based on this centroid, but they are dirty. So now once we recalculate, we're going to have a much better centroid. And you can see in here, we have 59, 20.59, 40.06, 75.18, 72, because we are recalculating 23 and 13 and 87 to 7. Right. Now, let's run one more iteration. You can see we have some more changes in the refinement of the cluster, and you can see the points, the centroids are moving even further to form a better one. So the whole process keep going. Let's see, we are still now. If we see this point has been now fixed, so this centroid is not moving. However, the second last centroid is still changing because the algorithm is finding a better place for that centroid, so it can group points better than the previous iteration. And even our first point is also changing, so that's good. So now you can see still changing up to this point. Keep changing it, and you can see the coloring scheme. By the way, you can see the coloring scheme is changing as well, and you're gonna see it in the behavior. That point, blue points are more, and in each iteration, even a small. So you can see this green point, which is just next to this blue. Now in the next iteration, that has been changed to blue, right? So that's the whole point of watching it on the graph. Now in this one, so because this is a random allocation, so sometimes it takes more time to convert, so things are keep moving. Now the first point we can see is now converged, like first centroid is not changing and last centroid is not changing. And the funny thing, we have reached, let me see what point we have reached to this point. Yeah, on the sixth iteration we reached to our converging point. And how would I know? Because my centroids are not moving anymore. So you can, if you can see the iteration 6 and the result of iteration 7, our centroids are fixed. Now I can see one more iteration to see whether it has been changed or there's anything that that is changing. Now there is nothing. You can see in the 3 iterations. So that's the indicator that the algorithm has converged. But like I passed the parameter 10 because I want to run 10 iterations. So the algorithm is keep running, but it is not changing anything. So that's the point where we reach to the local minima, where our cluster has been formed. So that's the best cluster we can get based on our data. And you can see the randomness of the points and the efficiency of the K-mean clustering, how quickly it is converging. Like in the 6th iteration, the algorithm has converged to local minima. Right. So the last point, there's no change in the last one as well. So that's the graphical representation of K-mean clustering. Obviously, we run it for a small point. Now let's run it for a little bit bigger one. So we are generating 1,000 points, and obviously it's a 2-dimensional. So we are converting it into two-dimensional array. Sorry, I need to change the above one. Let me keep it as it is. I'm just going to change this one now to 1,000, and I'm going to convert it into 2-dimensional array. And obviously, once we convert into 2-dimensional, the value of the length of the array is going to be half. So that's why I'm actually, if I'm generating 1,000 points, when I convert into the 2-dimensional array, it's going to be the 500 length of 2-dimensional point. Simple calculation. All right, so let me just run again. And now what I'm going to do, just to make things interesting, I'm going to now change, I'm going to pass the value of k to 5. I want to divide my points of generate 5 cluster. Obviously, I need to pass one more color. Let me see what color I can pass that's more attractive. How about so we have yellow, we have, let's pass brown, right? Or let me pass some dark color because I already have a color code on the other screen. Let me pass indigo. Indigo, right? Yeah. So all good. So we are just now going to run the show. Now that is going to take some time because we have increased the point, but not like forever. It's going to take a little bit more time. You can see the iteration is running now. Which is quite decent because it's not going to take much time and it's pretty fast, but obviously we have now more points, so it's going to take, and that's where we need to look at the efficiency, or we need to look at the optimization. K-mean clustering is really efficient, but obviously it has the challenges in order to find the initial center points, or generating the initial cluster, because initial cluster are going to be random base. So once it start refining it, that point is going to take some time, but then as soon as it start coming closer to the local minima, the speed will be efficient compared to the start of the algorithm. All right, so we are reaching, I think, yeah, we are done. So let's come in. Let's see why it did not. Sorry, that was my mistake. We have increased the value of k, but we didn't pass the parameter. Why? Did I run the same algorithm? Let me see. I think I made some changes. All right, so let me show you why it's not actually, because we didn't pass the parameter, we passed the static value. I think that's now good. Let's run it now. By the way, you can see it's not taking a lot of time with, although we have 500 points with two-dimensional, and later I'm going to even increase the point. We just see that how it works against those points, right? So let's run it, and then we come towards some really large data that we'll see that how it work against that data set. So now it's running again. So I believe we are reaching to, by the way, while it's running, we can see the changing in the centroid. So you can see it started with 80, 26, and then in the next one, it has changed to 61 and 12, and then 43 to 10, 43 to 11, and then it has changed to 86 to 25, because the points are continuously moving, or the centroids are continuously moving based on the the centroid location. All right, so now you can see we have 5 color, and obviously things are more complicated than the previous one, but now considering we already have a base, so you can easily understand, right? So these are, the first one obviously is the random point. So you can see we just pick 5 random point, and the location of these black dots, which are showing this location of centroid, that tell us that we are picking random points, right? So these two are very close, and these 2 points, but as soon as we run the iteration, you can see the algorithm immediately shift the points to their right location, or towards the right location. All right, and then the iteration keep going, refining the centroid location and allocating the color. Now you can see we have 5 groups, so we can see 5 colors or into our points. Let me quickly see where it is converging. So up to iteration 5, there is no convergence. Let's see the 6. So from the 6th iteration, I can see the values start coming similar. So that value is similar. 41, that one similar as well, 43 is similar, and there we go. At iteration 6, we are reaching to the point of convergence, and you can see it like there is no change from iteration 5 all the way till iteration 7. So you can see, although we are passing 10 iteration, but in the half of it, it just converts the classification of these points to their right cluster. So that's the K-mean clustering with the real representation and with the Euclidean distance demo. Hopefully you like it and understand now the concept. I'm going to upload this notebook as well into my Git. Please feel free to download. The source code is open. Use it for your own work without any licensing issue. And in the next video, I'm just gonna discuss another version of this function where we are just displaying the textual data. So the whole thing which is coming now graphically, in the next video we'll discuss it from the numerical perspective, and we also run it against some large data set to see the performance. Thanks for watching, and I'm gonna see you in the next one. Stay tuned.